Alright, it's a couple days late, but here is your first day one pre-lecture video. Well, maybe I should call this the post-lecture video. So what I want to do today is I just want to do a sort of short proof to show that the expression we talked about in class the other day, the expression for a traveling periodic wave, actually satisfies an important physics equation, which is called the wave equation. And this is what the wave equation looks like. It's actually a differential equation. Notice, of course, it's one of those partial derivatives, so I know that you probably think it looks extra complicated because of the notation, but remember we covered that notation in class, and it's really not that bad. We're just taking derivatives of a function that depends on more than one variable. So we treat the other variable as a constant. So basically in physics, the wave equation describes any function, you know, for instance here, y of x of t, that satisfies this equation is found to travel as a wave with a speed of v. So this v squared here refers to the speed of the wave. And so what I want to do is I want to show that the expression we worked with the other day actually does satisfy this equation. So let's get started. So this was our expression for our traveling wave. And so what we need to do is we first want to find the second derivative with respect to time of the expression, which would correspond to acceleration, by the way. And we did do this in class, but we're going to do it again. Remember that, of course, we have to take the derivative twice. The partial derivative is just acknowledging that this function y also depends on another variable x. We're going to treat that x as a constant during the time that we're taking the derivative with respect to time. So we first take the derivative of the cosine, which gives us minus the sine. Then we have to take the derivative of the argument of the sine, which is kx minus omega t, which is going to give us a minus omega. So our first derivative is omega a sine of kx minus omega t. When we take the second derivative, we're going to get derivative of sine is cosine, and then take the derivative of the argument of the cosine, which gives us a minus omega, which gives us minus omega squared a cosine kx minus omega t, which, notice, we could also write this is minus omega squared y. All right, okay, so we did that side. Let's look at the other derivative. So I'm just going to write this again to remind us that this is the expression we're taking the derivatives of. So now we want to find the second derivative with respect to x. So first we have to take the first derivative. So derivative of cosine is minus the sine again. This time we're taking the derivative of the argument of the sine but with respect to x. So that's going to give us a k. So we get minus ka sine of kx minus omega t. Now I take the derivative again. Gives us the cosine kx minus omega t, and then using the chain rule it's going to give me another k, so that's a minus k squared a cosine kx minus omega t. So the second derivative is going to be minus k squared y. And remember also we found that the second derivative with respect to time was minus omega squared y. Okay, so those are our results so far. Now let's remind ourselves of the wave equation, which was d squared y dx squared was equal to 1 over v squared dy dt squared. So if we rearrange, we would actually find that d squared y dt squared over d squared y dx squared should be equal to v squared. So let's test that. So our t squared gives us minus omega squared y. Our second derivative with respect to x gives us the minus k squared y. The y term cancels out. This gives us omega squared over k squared. Is this equal to the velocity of the wave squared? Well, let's see. Omega is 2 pi f, and k is 2 pi over lambda, so that's squared. The 2 pi's are going to cancel out, and I'm going to get f times lambda squared, which is equal to v squared. So, yes, it's equal to v squared, which we found. And so, basically what we have found is that this expression that we've been working with for a traveling wave does satisfy the wave equation. So it does signify or physically describe a traveling wave and does satisfy the partial differential equation that defines a traveling wave as well. So it might not seem that interesting, but it's something that I think you should see, and this way we didn't have to take class time to do it.